Okay, so it seems like we know how to figure out the percent mass from a molecular formula. So let's start there. Let's go through an example, just something simple. We'll use methane. So that's going to be CH4. So we've got carbon and hydrogen. Nice and simple to start out with. Carbon, what is the molar mass of carbon? Well, it's 12. 12 grams per mole. Hydrogen, it's going to be 1 gram per mole. So altogether, that's going to be 12 plus 4 times 1, which is 16 grams per mole. So if I wanted to figure out the percent mass of each of these, I would take that 12 grams per mole, times the number of carbons in the formula, which is 1, divided by the total molar mass, which is 16. And that's going to give me 0.75 or 75%. And I'm going to do the same thing with the hydrogen, then we're going to work backwards from there. So the hydrogen is 1 gram per mole, but there are 4 of them. So divide that by 16 grams per mole. That's going to be 0.25 or 25%. All right, so that's going to percent mass. Now we want to work from percent mass back to a molecular formula. In order to do that, we're going to say, all right, I've got carbon, I've got 75%, and hydrogen, I've got 25%. All right, so what can I do here? Well, this is percentage of a mass, so there would be really no difference from saying percent mass to saying, well, how many grams would there be of carbon in a 100 gram sample? In 100 grams of the total thing, 75% of that, what would that be? Well, that'd be 75 grams. 25%, well, that would be 25 grams. Add those together, 100 grams, perfect. So what we can do is we can convert from the percentage to a mass just by assuming that we have a 100 gram sample. It's just to switch out the units to make something that we can actually use. Okay, so I've got 75 grams of carbon, 25 grams of hydrogen. Now how do I convert that back? Well, the first thing I need to remember is that this ratio right here, this 1 to 4 ratio of carbon to hydrogen, that is independent of mass. It has everything to do with number of molecules and nothing to do with mass. So what do I need to do to get to number of molecules? Well, I can use moles. So remember, moles is just 6.022 times 10 to the 23rd molecules of a thing. So converting from grams to moles will give me that numerical ratio between the two of them. So I'm going to convert 75 grams, so I'm going to bring this down here. So I've got 75 grams of carbon, and we've been doing this, so this shouldn't be too much extra work. It's just putting it in a different order. So 75 grams of carbon, how many moles is that? Well, I go 12 grams per 1 mole, and then 25 grams of hydrogen, and that's going to be 1 gram per 1 mole. Now 75 divided by 12, what is that going to be? 5 divided by 12. Oh, wrong numbers. 75 divided by 12. That's going to be 6.25 moles. Now, hydrogen, 25 divided by 1, well, 25 moles. Okay, so now I have a number of moles, but I need to convert it into a ratio. I need to know how many moles I have, you know, on a 2 to 1 or a 3 to 1, how many of each do I have? In order to do that, I'm going to take my smallest number here. So in this case, that's going to be the carbon. And I'm going to divide everything by that number. So 6.25 moles divided by 6.25 moles is just going to be 1. So then I can take that 25 moles and do the same thing. So 25 moles divided by 6.25 moles equals 4. So what this means is that for every 1 carbon, I have 4 hydrogen. So with all this together, I get 1 carbon, 4 hydrogen, or just CH4. That's how I convert it back. Now, I've had some questions about, what about this reciprocal thing? Well, in this case, this worked out really nicely. We've got CH4. Our lowest ratio is a 1. But what would it look like if it wasn't? What would it look like if our lowest ratio was 2? So let's look at that. Okay, here we have aluminum nitride. That's going to be 3 aluminums for 2 nitrogens. So our lowest ratio is not going to be 1. So let's do the same thing. We'll work backwards and then forwards so that we can really see this whole thing play out. So aluminum nitride, first we need to get our molar masses. Okay, nitrogen has a 14 grams per mole. Aluminum has 27 grams per mole. And together, we have 109 grams per mole. So, first, let's find our percent mass. For aluminum, 27 grams per mole, that's going to be 27 times 3 aluminums divided by the total 109. That's going to give me 74.3%. Same thing down here. It's going to be 14 times 2 divided by 109. It's going to give me 25.7%. That rounds out nicely. Okay, so then, working it backwards, I'm starting with 74.3% aluminum and 25.7% nitrogen. How do I figure that out? Well, the same thing. So 74.3%, let's convert that all to grams by saying my sample is 100 grams. So 74.3 grams instead of 74.3%. The nitrogen, 25.7 grams. Okay, so down here, 74.3 grams of aluminum times, now I need to get rid of the grams, so grams of aluminum on bottom, moles of aluminum on top, 1, and then grams is going to be 27. Same thing for nitrogen, 25.7 grams of nitrogen. Then it's going to be grams of nitrogen on bottom, moles of nitrogen on top. It's going to be 14 to 1. So 74.3 divided by 27 gives me 2.75 moles. And here it's going to be 25.7 divided by 14. That's going to give me 1.84 moles. All right, what's my lowest number here? Well, that's going to be my nitrogen, 1.84 moles. So then in order to get a ratio, in order to get my aluminum to nitrogen ratio, I need to divide everything by that 1.84. So I'm going to take 1.84 divided by 1.84. Obviously, that's going to be 1. Then I'm going to take my 2.75, divide that by 1.84. Let's give us a little divider here so I can see what's going on. So 2.75 divided by 1.84. Now that gives me 1.5. Now I can't have 1.5 of an atom. So my ratio here couldn't be Al 1.5N, that doesn't make sense. That's impossible. So I need to get these to whole numbers. How am I going to do that? Well, 1.5, what's the closest whole number? Well, that's going to be 3. So that reciprocal thing is saying 1 and 1/2. The reciprocal of 1/2, is just 2. So if I multiply everything by 2, then I'm going to get my ratio. So this times 2 equals 3, this times 2 equals 2. So then my ratio is Al3N2. There we go. There's my molecular formula. Okay, but what about something that doesn't come out so clean, like a 1/2? In that case, we just use the reciprocal, which is just when we flip it. But how about something like this? O5Cl3. Well, if I wrote these out, if I did all that work over there, the ratio I'd end up with is O would be 1.667, Cl would be 1. Well, 0.667, if I put that into fraction form, I have 1 2/3. In order to get back to my actual molecular formula here, I'm going to multiply by the denominator, okay? So if I multiply everything by 3, well, this 1 times 3 gives me 3. 1 2/3 times 3 gives me 5. So that would lead me back to O5Cl3. So whenever you go through this, if you end up with something that is not a whole number, you need to get it back to a whole number by multiplying by the denominator. Okay, let's do one that's a little more challenging, where we don't get to go from the forward end and then go back. We'll do an actual example. This will be number 5 from the second page. This is asking us to both find the empirical formula and the actual molecular formula. So remember, the empirical formula is just the ratio of atoms. The molecular formula is the exact amount that are in each molecule. So number 5 gives us carbon at 62%, hydrogen at 10.4%, oxygen at 27.5%, and a molecular weight of 58.1. Okay, so again, our first step is going to be saying, instead of using percentages, I want to use mass. I've got a 100-gram sample. So then this becomes 62 grams, this becomes 10.4 grams, this becomes 27.5 grams. Our molecular weight stays this. This is going to be our total weight per molecule. Keep that in mind. So I need to take 62 grams, I need to convert that into moles. Same thing with the hydrogen and same thing with the oxygen. So I'm going to do that down here. 62 grams of carbon times the molar mass of carbon. We should all know this by now. This will be 12 grams per 1 mole. It's carbon. And then 10.4 grams of hydrogen. And then I'm going to put grams of hydrogen on bottom, moles of hydrogen on top. It's just a 1-to-1 ratio. And finally, 27.5 grams oxygen times 1 mole of oxygen for 16 grams of oxygen. Okay. Okay, for carbon, I get 5.167. For hydrogen, I get 10.4. And for oxygen, I get 1.719. All right, what's my lowest one? Clearly, oxygen, 1.719. Let's go ahead and circle that, keep it in mind. then set everything up, divided by that number specifically. So this, let's get that out of there. Let's just make a dividing line, set them up fresh. 5.167 divided by 1.719, 10.4 divided by 1.719. Obviously 1.719 divided by 1.719 will equal 1. For the rest of these, I'm going to plug them into my calculator. That will give me 6.05 for hydrogen. This one. And 3.006 for carbon. Now, these are all close enough to 0 that we're just going to round them. Round it to the first decimal place. Otherwise, just the rounding that we do over here is really going to give you some funky results, okay? So this, 3.006, round to 3.0. 6.05, round to 6.0. Okay, so that means I've got C3H6O. There we go. That's nice and convenient. But now we need to go molecular weight. So this is 12, 1, and 16. So what's my total molecular weight of C3H6O? That's going to be 12 times 3 plus 1 times 6 plus 16. That'll be 58. Well, look at that. Our molecular weight is 58 here, 58.1 right here. Good enough. Okay. But what if it wasn't? So the answer for this one is C3H6O. But what if my molecular weight was something other than 58.1? Well, what else could it be? Other options for this particular problem, 58.1 could have become 116 or 174. So let's look at those. So if I had a molecular weight of 116, what would I have to do? Well, I would take that molecular weight, the molecular weight that's given to me in the problem, 116, and I would divide it by the molecular weight that I found, 58. 116 divided by 58 is going to give 2. When I get that number, this 2 right here, that's just going to tell me that I need to multiply everything in this problem by 2. All it's saying is that the molecular weight of one of these is double just that base value. This is the lowest possible ratio. I can't get any lower than this because it's 3 to 6 to 1. I can't go less than 1. But I could have a ratio that is greater than that without realizing it. So if my molecular weight was 116, and then I would have a C6 H12O2. And that would be 116. This is a possible molecule. This is something that could very well exist, and it would be different than this one. Okay. Now what about 174? If I was given a weight of 174, well then I would still take that number divided by the base molecular weight, 58. And in this case, that'll give me 3. If I get 3, then I have to multiply everything in here by 3. So 3 times 3 is going to be C9. 3 times 6 is going to give me H18. And 3 times O is O3. And so that would be for 174. So if I ever get a molecular weight that is larger than this base one that I come out with, I'm just going to divide it by whatever I calculated here to figure out how much I need to multiply my formulas by. Okay. If there's any questions, send me an email, ask me on the Microsoft Teams, or just ask me on Google Classroom. So far, you guys have been pretty good about reaching out. Well, most of you. If there's anything else, if you're having any troubles, let me know.